Hello and welcome to MATLAB Programming for Numerical Computations. We are in Module 2, Errors and Approximations. In Lecture 2.1, we introduced ourselves to errors and approximations and how they arise in numerical computations. In Lecture 2.2, we considered truncation errors. We have taken the example of Maclaurin series expansion of e to the power a and showed how including additional terms from the infinite series improves the accuracy of the approximate method that we use. In this lecture 2.3, we are going to consider another type of errors which are known as round-off errors, and we will see the trade-off between round-off and truncation errors. Thereafter, we will talk about another type of method known as iterative method. So we will take the example from numerical differentiation. So instead of limit h tends to 0, in the finite precision machine, we can calculate f dash of x approximately as f of x plus h minus f of x, the whole thing divided by h. This also can be derived from Taylor's series. This is something that you would have done in your 12th grade or your first year math class. We are not going to bother ourselves with how to derive these equations. We are going to use these equations in MATLAB. We are going to just remember what this particular term means, order of accuracy, when it comes to numerical methods. Okay, so let's go to MATLAB and do this numerical derivative problem. Okay, so the example that we will solve in today's lecture is going to be tan inverse of x. We want to find d by dx of tan inverse of x at x equal to 1. Okay, so let's look at what the command in MATLAB is to get tan inverse, and that command is a tan. So if we do a tan of 1, we will get the result as pi by 4, and that's what we get when we put a tan of 1. Let's check this by typing pi by 4, and as you can see, a tan of 1 is indeed pi by 4. Okay, so now let's look at what we need to do. We need to use this particular approximate method in order to get the derivative. Let's define our a. Let's clear all. Let's define our a equal to 1. Our true value of the differential, true val, is going to be equal to 1 divided by 1 plus a squared. Okay, remember the brackets. So the true val is equal to 0.5. So the d by dx of tan inverse of x at x equal to 1 is going to be equal to 0.5. Now we want to compute this numerically, and the way we will compute this numerically is we will first define our h. Let's start with h equal to 10 to the power minus 2. Approx val is going to be a tan x plus h, or rather a tan a plus h minus f of x, which is a tan of a tan of a. Now the whole thing in brackets divided by h. That's going to be our approx val. The error is going to be nothing but ABS value of true val minus approx val, and the error is 0.0025. Let's do this again for a different value of h, and that value of h is, instead of 10 to the power minus 2, we will take that value as 10 to the power minus 3. Okay, we will again calculate our approx val in the same manner, and we will calculate our error also in the same manner. Okay, so what we see is when we decrease our h by a factor of 10, our error is also decreasing from 2 into 10 to the power minus 3 to 2 into 10 to the power minus 4, which is again a factor of 10. Let's decrease our h further. So when we take the h as 10 to the power minus 4, approx val calculate in the same manner, error we calculate in the same manner. What we see is when we further decrease our h by a factor of 10, the error also further decreases approximately by a factor of 10. Recall that this is the consequence of the fact that the method is h to the power 1 accurate, which means that when we decrease the h by a factor of 10, our error decreases by a factor of 10. When we decrease h by a factor of 100, our error decreases by a factor of 100, so on and so forth. That is the meaning of the order of accuracy of any numerical method. Okay, so what we have done so far is made all these computations on the command prompt. Recall what we had said in the lecture on MATLAB functions and scripts. MATLAB script is nothing but running all these commands one after the other in a file. Okay, so what we can do is we can copy and paste all of these in a file, and that file will be a MATLAB script that will run our commands in a sequential manner. So let's edit the file. We'll call it numderiv. To calculate numerical derivative. So let's go here. Okay, h equal to 0.0001. I'm just pressing the up arrow key. When I press the up arrow key, we'll go over the previous commands that were there in MATLAB. Sorry, yeah, ERR. Okay. So these are the numerical derivatives for h equal to 0.0001. What we had also done is calculated this for two other values of h, and we will do that here again. We just copy pasted these things. Then this for h equal to 10 to the power minus 2, h equal to 10 to the power minus 3, and h equal to 10 to the power minus 4. Okay, and we will save this. We'll clear all to clear all the variables, and CLC will clean up the screen for us. Okay, so now what I will do is run this code numerical derivative numderiv. Okay, now when I run this code, I expect an error. I'll take a couple of seconds. You can pause this video right now, and can you spot what error we are going to get when we run this code? Okay, I will show you what happens when we run this code and what error we are going to get. So let me click on run. So when I run this, I get an error which says undefined function or variable a. We did not get this error earlier, we got this error now. Why is this happening? What does this error mean? What this error means is that the value of a has not been defined. Now, why do you think we got this error but we did not get this error earlier? The reason why we got this error is because just before typing numderiv, we had typed clear all, which meant that all the variables that were there in MATLAB's memory have been erased. As a result of this, we were getting this error. We will cycle through the various commands that we had input earlier, and we will see that when we started this particular module, we had a command a equal to 1. We also had a command trueVal equal to 1 divided by a squared. 1 divided by 1 plus a squared. We forgot to add this when we wrote this code. So let's go ahead and type this in also. And we will also have to type the trueVal. Okay, so now when we run this code, we should not get any error. Okay, so remember what we ended up doing, and this is one of the more common errors that I've found, at least people new to MATLAB make. So sometimes we forget that some of the variables have not been defined. This is how one should read whenever we get an error. This states, the first line after the error states that what the error actually is. The error is that the variable a is not defined. What we realized then is that earlier all our codes were running, and the reason why they were running earlier but they stopped running now is because we had given the clear all command. Then we realized that when we started this MATLAB session, we had given a equal to 1 and as well as computed the true val value. So those, when we insert in our MATLAB script and we run this, we are going to get the results as required. So let me run this and we will get these results as required. Now what I want to do is, why do I need to give this repeatedly in this particular manner? We want to now put it in a for loop, and the for loop will become for I equal to, say, 2 to 4 in this case. H is nothing but 10 to the power minus I. Okay, approx val, I will just copy and paste it over here, and error, I'll just copy and paste it over here. Okay, and I'll say end. I will delete this, save this. When I run, I'm going to get the same results. Again, let me run this again for you. NumDerif, and I'm getting the same results as I have been getting before. Okay. So next, what I want to do is I want to see how this error actually varies for a fairly large number of step sizes that we have taken. So instead of I going from 2 to 4, let me say I goes from, say, 2 to 7, let's say, for example. Okay, what I'm going to do also is I'm going to save my and h in two vectors, which I will call as h all I minus 1 equal to h, or all I minus 1 equal to r. So these are just for storing the results and plot error versus step size. We want to do a log-log plot of h all in the x-axis or all in the y-axis. Okay, and that is what we want to do, and we want to see that this is a linear straight line. Okay, so now let's run this and we get a straight line as seen over here. Okay, the reason why we get this straight line is because your f dash x, the error term, is of the order of h, which basically means when we plot the error against h on a log-log scale, it's going to be a straight line with slope of 1. The straight line slope is going to be the same as the order of the accuracy of the numerical scheme that we are going to use. Okay. Next, what we will do is this. Instead of carrying this out until 7, let's do this for a larger number of terms, but we'll do it in steps of 2, let's say. And let's go to from 10 to the power minus 2 to 10 to the power minus 14. I'll just make small changes in this code over here. Clear all, CLC, close all, and let me run the NumDerif code. Okay, and this is the result that we get. As you see over here, what we got when we decreased our h from 10 to the power minus 2 to 10 to the power minus 7, or in this case up to 10 to the power minus 8, we get a steady decrease in the overall error as the step size decreases. But after a certain point, when we decrease the step size, the error doesn't decrease anymore, but the error starts to increase. The reason why this happens is because of round of errors. You remember what we said in the first lecture is that there is a machine precision, there is a least count for that machine. At a certain point, it's the round of error that dominates, and beyond that point, the error increases. So when we are going to do numerical derivatives, we are going to start facing the issues of trade-off between round-off and truncation errors, and there is a step size which is going to be best for numerical derivatives. This is something that we are going to cover in the next module, in module 3 on numerical derivatives and numerical integration. Here I wanted to demonstrate to you that there is something called truncation error, there is something called round-off error, and then there might be trade-offs between these two errors which will result in some unique properties of some of the numerical methods. Okay, so to go and recap what we did in numerical derivatives, f dash of x we calculated approximately as f of x plus h minus f of x divided by h. We saw that the truncation error decreases with h. Truncation error on a log-log scale decreases linearly with h with a slope of 1. The machine precision determines how small h we can use. We can't use h to be really small because because of machine precision the round-off errors start to accumulate. What we have covered so far is what is known as direct methods. The first direct method was Maclaurin series expansion of e to the power a, which was covered in the previous lecture. In this lecture we covered another direct method which was computation of numerical derivatives. Direct method is nothing but an algorithm which directly computes a solution through a sequence of operations, a sequence of equations that we keep executing, but we execute them once through and we are done with it. That is how we are going to compute the solution using direct method. The second type of method that we are going to consider in this lecture is what is known as iterative methods. Iterative methods, we will start with certain initial guess and we will use certain steps repeatedly or iteratively to improve that initial guess until we reach a convergence. Let's take an example of iterative method. As I mentioned before, the example of iterative method that we are going to take is what is known as Heron's algorithm. Heron's algorithm is arguably one of the first iterative numerical algorithms that was known to man. This was discovered in around 17th century BC in Alexandria. It computes square root of 2 using an initial guess. Let's say the initial guess was 0.5. We use that initial guess and we iteratively use this equation. So x equal to half of x plus 2 by x is going to give us the next solution, and we will keep going with these iterations till we are convinced that we have reached a solution. So let's go to MATLAB and do this. Okay, we'll start with an initial guess of x equal to 0.5. And we are going to iteratively use this equation, which is the new guess of x is half of current value plus 2 by current value. So x, or let me just say x new, equal to 1 by 2 multiplied by x plus 2 by x. Okay, that's going to be x new. Now because this is an iterative method, we don't need to call it with another name. We can just call it with the same name as before in this particular example. So x is going to be average of x and 2 by x. Okay, so next value is 2.25. The value after that is 1.56. The value after that is 1.42, 1.4142. Okay, and if we repeat it multiple times, we are not going to get any more changes. So this is how an iterative method works. We start with an initial guess and we iterate on that initial guess till the solution reaches a desired accuracy. Let's put this all in MATLAB, edit, Heron algorithm. Calculate square root of 2 using Heron algorithm. So let's have our initial guess as x equal to 0.5. Say for I equal to 1 to, let's say we expect up to 25 iterations. Okay, x new is going to be equal to half multiplied by x plus 2 by x. Our error is nothing but ABS of x minus x nu, and our x equal to x nu. Okay, and yeah, so let's type this out. Maybe we should not do it for 25. We know that it converges very quickly, so let's just do it for 10 iterations and let's run this. Okay, so what we start off with, the error was 1.75, that is the error between, or the difference between x new and x old is 1.75, 0.68, 0.14, 0.007, 2 into 10 to the power minus 4, so on and so forth. So this is probably where we can say that we need to stop, and that is based on a tolerance value. So let's go and change this a little bit. Let's say a tol, the absolute tolerance value is 1.0 e minus 5. Okay, and instead of for, we will have a while loop. While ERR is greater than a tol, we will keep repeating these steps. So we will stop these steps when the error falls below the tolerance value. We also need to initialize the error, so we will just call the error, we'll just initialize it as 1. Okay, if we do not initialize this error, okay, so let's clear all. And here on algorithm. Okay, so as you can see, we started with a large enough error and we stopped at a certain value over here. Okay, and this is where we have used the while loop in order to compute the Heron's algorithm. If instead of x equal to say 0.5, if we were to give a value of x equal to 0.1, let's see what happens. Clear all, Heron algorithm, and again we converge to the desired solution in certain number of steps. As you can see over here, if the farther we are away from the true solution, the greater the number of steps we are going to require. Okay, so with that, I come to the end of this lecture. What we have discussed over here is we looked at a direct method, and then we looked at iterative method, and we looked at the criteria. When do we stop and say we have a solution? We will stop and say that when we have a solution is when the difference between x new and x old, the absolute value of difference, falls below a certain tolerance threshold. What we covered in this lecture was a direct method to compute numerical derivative and saw the trade-off between truncation and round of errors, and then we saw an iterative method in Heron's algorithm. Okay, that completes our lecture 2.3, and I will see you in the next lecture. Thank you and goodbye.